In a single megafactory in China, more than 50 million meters of fiber optic cable are produced daily, enough to connect New York to Los Angeles and back 3 times. Glass drawing towers, 40 meters tall, operate at temperatures of 2,000 degrees Celsius, transforming pure sand into glass threads thinner than human hair, yet capable of transmitting trillions of bits of information per second. But here's the billion-dollar secret that sustains the entire internet. The global fiber optic industry moves $400 billion annually, and every click you make, every video you watch, every message you send, travels through a network of 500 million kilometers of fiber optic cable, equivalent to 1,300 trips to the moon. The device you're using to watch this video is connected to infrastructure worth more than $5 trillion in submarine cables, telecommunications towers, and data centers. The sound is hypnotizing, the constant whisper of furnaces melting silica at volcanic temperatures, the hum of machines stretching molten glass at speeds of 2,000 meters per minute, and the absolute silence of light beams traveling at 300 million meters per second through glass crystals purer than diamonds. In 24 hours, a single factory produces enough fiber to connect 100,000 homes to high-speed internet. How is it possible that grains of sand transform into cables that carry 99% of all global internet traffic? How are billions of fiber optic connections manufactured with atomic precision at industrial speeds? And why does this secret process determine who will control the $2 trillion of the global digital economy? The answer is hidden in fiber optic megafactories, technological cathedrals where quantum physics and precision engineering unite to create the invisible nerves of digital civilization. Prepare to discover how billions of fiber optic connections are born from a process that transforms common sand into the backbone of the global internet. The history of fiber optics began in 1870, when Irish physicist John Tyndall demonstrated that light could be guided through curved water jets, but it was only a century later that this discovery would transform into the $400 billion industry we know today. The true revolution began in 1966, when Charles Cow of Standard Telecommunications Laboratories published a visionary paper proposing that ultra-pure glass fibers could transmit light over long distances with minimal loss. His research established that fibers with 99.999% purity could revolutionize telecommunications. The first commercial fiber optic was produced by Corning Glass Works in 1970, costing the equivalent of $1 million per kilometer. The initial process was so complex that a single factory produced only a few meters per day, using techniques developed for the space industry. The 1980s marked the commercial explosion. AT&T installed the first long-distance fiber optic system between New York and Washington, moving $10 billion in investments. Innovations in manufacturing processes reduced costs from $1 million to $1,000 per kilometer, making mass deployment viable. The Internet era of the 1990s created insatiable demand. Companies like Lucent, Alcatel, and Fujikura invested $50 billion in automated megafactories. The chemical vapor deposition (CVD) process enabled production of millions of meters daily, while continuous drawing techniques increased speeds to 2,000 meters per minute. The submarine cable revolution transformed the industry into a trillion-dollar business. Projects like the TAT-14 cable across the Atlantic cost $2 billion and used 10,000 kilometers of special fiber. Today, more than 400 submarine cables, worth $300 billion, carry 99% of intercontinental internet traffic. The modern era of fiber optics sustains a $5 trillion digital economy. Every smartphone, every video stream, every banking transaction depends on infrastructure that processes 500 million meters of fiber optic cable daily in factories that operate like Swiss watches with atomic precision. The process of transforming sand into fiber optic cable is a technological symphony that begins with silica purification, the purest material ever created by humanity. High-quality quartz sand passes through furnaces at 2,500 degrees Celsius, where impurities are removed to parts per billion levels. This ultra-pure silica is worth $10,000 per ton, compared to $50 for common sand. Preform manufacturing is where quantum physics magic happens. The chemical vapor deposition (CVD) process uses ultra-pure gases, silicon tetrachloride, germanium, and phosphorus, that cost $5,000 per kilogram. These gases are injected into rotating quartz tubes at 1200 degrees Celsius, depositing glass layers with atomic level thickness control. Each preform, a glass cylinder 2 meters long and 20 centimeters in diameter, is worth $50,000 and contains engineering information that took decades to develop. The central core has precisely calculated refractive index to guide light through total internal reflection, while outer layers create perfect optical barriers. The drawing process is where billions of dollars in technology unite. 40-meter-tall drawing towers heat the preformed tip to 2000 degrees Celsius, creating a molten glass drop. Laser control systems monitor fiber diameter with nanometer precision, maintaining thickness of 125 micrometers, thinner than human hair. Fiber is drawn at speeds of 2,000 meters per minute through controlled cooling systems. $5 million graphite furnaces each maintain uniform temperature, while computer-controlled tension systems ensure the fiber doesn't break. Any microscopic variation can ruin kilometers of product. Protective coating is applied in real time through UV curable polymers, costing $100 per kilogram. $2 million ultraviolet curing systems harden the coating instantly, creating protection against moisture and mechanical stress. Quality tests verify optical attenuation, dispersion, and mechanical resistance every meter produced. Modern fiber optic megafactories are impressive examples of automation incorporating technologies that seemed impossible 2 decades ago. $100 million artificial intelligence systems monitor more than 1,000 parameters simultaneously, from chemical purity to mechanical tension, optimizing production to maximize yield and minimize defects. Plasma deposition technology revolutionized preform manufacturing. $50 million plasma systems operate at 10,000 degrees Celsius, creating conditions that enable deposition of layers just atoms thick. This atomic precision is essential for fibers transmitting data at terabit speeds. State-of-the-art drawing systems use laser control and computer vision to maintain nanometric tolerances. $10 million optical sensors measure fiber diameter 1,000 times per second, automatically adjusting temperature and speed. Any deviation of 1 nanometer can compromise optical performance. Innovations in materials include erbium-doped fibers for optical amplification and photonic crystal fibers that manipulate light at quantum level. These special fibers cost $1,000 per meter and are essential for long-distance communication systems connecting continents. Automated testing technology verifies every meter of fiber through optical time domain reflectometry, OTDR. $20 million systems inject laser pulses and analyze reflections to detect microscopic defects. Defective fibers are automatically rejected and recycled. Advanced robotics handles fibers with sub-micrometric precision. $5 million robotic arms each wind fibers onto 20-kilometer spools without introducing stress or microbends. Computer vision systems inspect fiber surface looking for defects smaller than 1 micrometer. The device you use to watch this video receives data through fibers produced in these megafactories. Every pixel on your screen, every sound you hear traveled through glass crystals purer than any natural material, manufactured with precision exceeding the semiconductor industry. Quality control in fiber optic manufacturing is more rigorous than space component production, as each microscopic defect can compromise billions of dollars in telecommunications infrastructure. $50 million laboratories equipped with mass spectrometers analyze chemical purity at parts per trillion levels, purity superior to pharmaceutical distilled water. Optical attenuation tests verify that fiber maintains perfect transparency over kilometers. $100 million test systems inject laser light at multiple wavelengths, measuring losses that must be less than 0.2 decibels per kilometer. Any fiber exceeding this limit is rejected, representing loss of $1,000 per kilometer. Chromatic dispersion analysis examines how different wavelengths propagate through fiber. $20 million equipment measures dispersion with picosecond per nanometer per kilometer precision. Fibers for high-speed systems must have zero dispersion at 1550 nanometers, the telecommunications standard wavelength. Mechanical resistance tests subject fibers to extreme stress to simulate decades of use. $5 million testing machines apply tensions up to 2% of length, while environmental chambers simulate temperatures from -40 to +80 degrees Celsius. Fibers must withstand 25 years of operation without degradation. International certification through organizations like ITUT and IEC ensures global compatibility. Interoperability tests cost $10 million annually, but guarantee fibers work perfectly in any worldwide system. One certification can be worth $100 million in government contracts. Complete traceability documents every production step through industrial blockchain. Each meter of fiber has digital identity recording manufacturing parameters, test results, and quality history. This traceability is essential for $2 billion submarine cables that must operate 25 years on ocean floors. The fiber carrying this video to you passed through more than 100 different tests, each verifying specific aspects ensuring perfect data transmission. Every photon of light forming images on your screen traveled through a medium purer than any natural crystal. The fiber optic industry leads the digital sustainability revolution, as each kilometer of installed fiber replaces tons of copper cables, reducing energy consumption by 80%. Optical transmission consumes only 1/10 the energy needed for equivalent electrical transmission, saving $50 billion annually in global energy costs. Glass recycling programs recover 95% of material from discarded fibers. $10 million special furnaces reprocess optical glass, transforming old fibers into raw material for new preforms. Each recycled ton avoids extraction of 2 tons of high-purity quartz sand. Energy efficiency of modern furnaces represents revolutionary advancement. $20 million heat recovery systems capture 80% of thermal energy, reusing it for material preheating. Green hydrogen burners eliminate carbon emissions, transforming factories into carbon-neutral operations. Material innovations include preforms manufactured with synthetic silica produced through clean chemical processes. This artificial silica eliminates mining necessity, reducing environmental impact by 90%. Chemical synthesis processes cost $50 million per factory, but create materials superior to natural quartz. Closed-loop water management recycles 98% of water used in cooling. $5 million purification systems produce ultra-pure water from recycled sources, while reverse osmosis technologies recover water from chemical processes. Digitalization sustained by fiber optics avoids emission of 2 billion tons of CO2 annually through remote work, video conferencing, and digital services. Each kilometer of installed fiber eliminates need for thousands of physical trips, creating digital circular economy worth $300 billion annually. Renewable energy programs power 70% of modern operations. Solar panels and wind turbines provide clean energy for furnaces and drawing systems, while storage batteries ensure continuous operation. Some factories generate surplus energy sold back to electrical grid. The industry's biggest challenge was the attenuation problem. Initial fibers lost 99% of light in just 1 kilometer, making long-distance communications impossible. The $100 billion solution came through development of ultra-pure glasses with impurities less than 1 part per billion, reducing attenuation to 0.2 decibels per kilometer. The production speed issue nearly made mass manufacturing unviable. Traditional systems produced only 100 meters per hour, insufficient for global demand. Development of 40-meter drawing towers and induction heating systems enabled speeds of 2,000 meters per minute, increasing production 1,200 times. Microscopic variations in fiber diameter created reflections compromising data transmission. $50 million laser control systems monitor diameter with nanometric precision, adjusting temperature and speed 1,000 times per second to maintain tolerances of plus or minus 0.1 micrometer. Mechanical stress problems during winding caused microfractures, reducing lifespan from 25 to 5 years. Development of controlled tension robotic systems and special spools with optimized curvature eliminated stress, ensuring decades of operation without degradation. Moisture contamination during manufacturing created absorption points, increasing attenuation. Class 10,000 clean rooms with 0.1% humidity control and inert gas purge systems eliminated contamination, maintaining perfect optical purity. Global demand fluctuations created cycles of overproduction and shortage, costing billions in idle capacity. $100 million artificial intelligence systems analyze global demand patterns, optimizing production to minimize waste and maximize utilization of billion-dollar equipment. Each overcome challenge transformed the industry into a more efficient machine for connecting the world, proving technological innovation can overcome fundamental physical limitations and create infrastructure sustaining digital civilization. Fiber optics is secretly the backbone of a $5 trillion digital economy, redefining how we live, work, and connect. Submarine fiber optic cables worth $300 billion carry 99% of all intercontinental internet traffic. Every Google search, every YouTube video, every banking transaction travels through glass crystals on ocean floors. The video streaming industry, valued at $200 billion, would be impossible without fiber optics. Netflix, Amazon Prime, and Disney Plus transmit petabytes of data daily through networks using 100 million kilometers of fiber. Every second of 4K video you watch requires transmission of 25 megabits through fibers thinner than human hair. Data centers worth $500 billion fundamentally depend on fiber optics for high-speed interconnection. Each Google, Amazon, or Microsoft data center uses thousands of kilometers of internal fiber to connect servers at terabit speeds. The device you use to watch this video is connected to this infrastructure through fibers that cost millions to install. Telemedicine, a $300 billion market, revolutionizes healthcare through fiber optics. Remote robotic surgeries require latency less than 1 millisecond, possible only through dedicated fibers. Medical imaging systems transmit gigabytes of medical data instantly, saving lives through remote specialized consultations. Autonomous vehicles, an $800 billion industry, depend on ultra-fast communication through 5G networks sustained by fiber optics. Each autonomous car processes terabytes of sensor data, communicating with urban infrastructure through fibers, ensuring millisecond decisions. The global financial industry of $100 trillion operates through dedicated fiber optic networks. High-frequency trading uses special fibers, reducing latency by microseconds, where each saved nanosecond can be worth millions in competitive advantage. Fiber cables between New York and London cost $500 million to save 5 milliseconds. Remote education, accelerated by pandemic, connects billions of students through fiber optics. Universities transmit real-time classes to millions of students, democratizing education through infrastructure, costing trillions to build but connecting knowledge globally. Every click you make, every word you type, every image you see travels through a fiber optic network representing humanity's greatest engineering work. 500 million kilometers of pure crystal connecting every corner of the planet. The future of fiber optics is being revolutionized by quantum technologies that will transform communications on planetary scale. Quantum fibers costing $1,000 per meter will enable absolutely secure communication through quantum entanglement, creating networks physically impossible to intercept. This technology will sustain a $500 billion cybersecurity economy. Optical computing will replace electronic processing in high-performance applications. Photonic processors will use light instead of electricity for calculations, increasing speed 1,000 times while reducing energy consumption by 90%. $100 billion optical data centers will process artificial intelligence through light beams. Photonic crystal fibers will enable light manipulation at atomic level. These special fibers, costing $10,000 per meter, will create optical devices functioning as light transistors, enabling fully optical computers operating at light speed. Space fiber optic networks will connect satellites in orbit through laser beams. Constellations of 10,000 satellites will use inter-satellite optical communication to create low-latency space internet. This $100 billion infrastructure will provide instant global connectivity. Real-time holography will require fibers with exabit per second capacity. Development of multi-core fibers with hundreds of parallel channels will enable transmission of three-dimensional holograms, revolutionizing entertainment, education, and communication. Each fiber will cost $100 per meter, but transmit virtual reality indistinguishable from physical reality. Quantum medicine will use special fibers to transmit quantum states of biological molecules. Remote quantum diagnostics will analyze DNA and proteins through fibers preserving quantum coherence, revolutionizing personalized medicine through analyses impossible with current technology. Future smart cities will use trillions of sensors connected by fiber optics. Every traffic light, every building, every vehicle will be connected through urban neural networks processing zettabytes of data in real time, optimizing traffic, energy, and resources through distributed artificial intelligence. The device you use today is just the beginning. Future brain-computer interfaces will use biocompatible fibers to directly connect neurons to global networks, creating digital collective consciousness sustained by fiber optic infrastructure connecting human minds on planetary scale. The extraordinary journey of fiber optics, from grains of sand to the nerves of digital civilization, represents the most impressive technological transformation of the modern era. What began as experiments with light and glass evolved into a $400 billion industry that literally connects every person, device, and idea on the planet through 500 million kilometers of pure crystal. Each meter of fiber optic cable emerging from these mega factories carries decades of scientific innovation and trillions of dollars in digital infrastructure. The process transforming common sand into cables capable of transmitting all human information is testament to our species' capacity to manipulate matter at atomic level to create technologies transcending physical limitations. The technological complexity of modern fiber optic factories, hundreds of millions of dollars in investments in equipment operating with nanometric precision, furnaces recreating stellar conditions to purify glass beyond natural perfection, demonstrates how the pursuit of perfect connectivity can generate innovations redefining the limits of possibility. Fiber optics is not just a transmission medium, it's the nervous system of digital civilization, the invisible infrastructure enabling ideas, knowledge, and creativity to flow instantly across continents and oceans. Every pixel on your screen, every sound you hear, every digital human connection is possible thanks to this crystal network operating at light speed. The impact of this industry transcends economic numbers, touching fundamental aspects of how our species communicates, learns, and evolves. The capacity to transmit information at light speed through media purer than any natural material positions fiber optics as the technology defining the future of human collective consciousness. How incredible to discover that every click, every video, every message you send travels through glass crystals purer than diamonds. The next time you connect to the internet, remember the extraordinary journey your data takes through 500 million kilometers of fiber optic cable connecting the entire world. What impressed you most in this exploration of fiber optic mega factories? Was it discovering that the internet depends on sand transformed into pure crystal, that each fiber is thinner than hair but carries trillions of bits? Or perhaps that billion-dollar submarine cables connect continents through ocean floors? Leave your comment below and share from where you're watching. Your comment is very important so we can always bring new videos about how the things we know are made and that we often don't know how they're produced. Share the video with your friends and family, and don't forget to subscribe to the channel. Do you know someone who works with telecommunications, information technology, or who simply fascinates with the processes sustaining our digital era? Share this video and help spread knowledge about the invisible industries connecting our civilization. And if you're curious to discover more secrets of digital infrastructure, don't forget to subscribe to the Factory Made channel, where each episode reveals the hidden processes sustaining our connected world. What other components of digital infrastructure would you like to see unveiled? Processor manufacturing? Smartphone screen production? Or perhaps data center construction? Your curiosity could be the next episode we explore together in this fascinating journey through the world of industrial processes secretly sustaining our digital civilization. Special thanks to Corning, Prysmian, Fujikura, and OFS Vittel companies for making available technical materials and access to their industrial operations that made possible this detailed exploration of the fiber optic manufacturing world. Gratitude also to optical engineers, materials physicists, and telecommunications specialists who dedicate their careers to continuous improvement of these processes connecting humanity. We thank photonics research institutes and technical universities that share knowledge about optics, materials, and telecommunications, contributing to scientific advances benefiting all global communications infrastructure. Special recognition to fiber optic factory workers around the world who operate in extreme precision environments to produce the millions of kilometers of fiber literally connecting our civilization, demonstrating dedication and expertise making our digital era possible. And most importantly, our sincere thanks to you, who dedicated your time to follow another exploration of the factory-made universe. Your curiosity and interest are the fuel motivating us to continue unveiling secrets behind industrial processes shaping our digital infrastructure and connected future. Continue with us on this journey of discoveries. Explore our other videos about industrial processes and discover how seemingly simple technologies hide operations of surprising complexity and precision. At Factory Made, each story is a celebration of human ingenuity and the magic of industrial transformation connecting our world. Research and script by Factory Made team. Transforming curiosity into knowledge, one industrial process at a time. The next time you connect to the internet, remember the incredible technological journey that transformed simple grains of sand into ultra-pure glass crystals carrying every bit of digital information, connecting minds and hearts through a global network operating at light speed.